we continue our discussion on support vector machines and how we move more towards solving the problem of the optimization problem of finding the largest gap decision surface. So, for a quick recap, support vector machines want to find margins with assumption is the decision surface is linear. We have support vectors, which are the data samples which are closest to the decision surface, whether it is on the positive side or on the negative side. And these are the ones which define the equation of the boundary. We have also seen that the geometric margin for the decision surface defined by WB is given by this equation. Gamma for the ith sample is found by yi multiplied by w divided by the norm of w and the product with xi plus the intercept b divided by the norm of w. This division by norm of w gives us the geometric margin, and for a whole set of examples we find this minimum geometric margin value. We computed this for all the m samples, and the minimum gives us the final geometric margin for the decision surface. Now, so we now want the how actually this optimization problem is defined. The SVM classifier aims to maximize the gap or the margin. This we have seen in our examples and also in terms of the functional and the geometric margin. So, the optimization problem to find this classifier with maximum separation between positive and negative samples, we write it as follows. The we want to maximize the geometric margin gamma under the constraints that the yiwtx plus b is greater than equal to 1 and also the norm is equal to 1. So, we are aiming to maximize the geometric margin under the constraints. So, we want to maximize gamma subject to each training example having functional margin at least gamma. So, that is the aim. Now, the norm equal to 1, which we had just seen here, the second constraint, W norm equal to 1. This ensures that the functional margin is equal to the geometric margin. As discussed in the previous videos, this means that all the geometric margins are also at least gamma. See, when we are looking at the data samples with the positive ones and the negative ones, and we have our the decision surface, suppose this is the one, and we are talking of the geometric margin. So, since this is the minimum of all the data samples, it also implies that all the geometric margins are at least equal to gamma or more than it. For the samples which are not support vectors, see, if we talk of these two support vectors, then all those samples which are not support vectors, this one or this one, the geometric margin is greater than gamma. Thus, the solution to this above optimization problem gives us WB or the decision surface such that the largest geometric margin is obtained with respect to the training set. We are maximizing this width. Okay, this is our gutter around the decision surface, and this we want it to be maximized. Now, we slightly transform our this optimization problem, maximizing of gamma, and write it as maximizing gamma hat division by the norm, which means we are writing it in terms of the functional margin. So, we want to maximize gamma hat by division by norm of W subject to each training example having functional margin at least y hat. See, this constraint also gets transformed because we have rewritten our maximization problem. So we further scale WB. You might recall that in functional margin, we can rescale WB and change the functional margin. So we're using that property and scaling it so that gamma hat equal to 1. So now the optimization problem becomes, it was maximizing gamma hat by the norm of W. So now it can be written as maximizing 1 by, because we have rescaled our WB to enforce gamma hat equal to 1. So we rewrite this as this. So, and this can also be equivalently written as minimizing the norm of W, or rather the square of the norm, because it doesn't change, minimizing norm or the square of it. We further include a half multiplier for the sake of mathematical convenience later on. So our are subject to the constraint, because now gamma hat has become 1. So we write it as this. So the final form of our SVM decision boundary can be written as minimizing under the parameterized by WB half of norm W squared, such that this WI WTX plus B is greater than equal to 1 for the positive samples, and this quantity is less than equal to minus 1 for negative samples, right? So this is the SVM decision boundary which we obtain by stating down the optimization problem and transforming it for making it mathematically more convenient. Okay, so thank you. Thanks for watching.